Okay, welcome everyone. I'm Nate Foster from Cornell. Really pleased to present our first, hopefully regular sort of Hangouts on Air seminar. We're doing it over Zoom, not Hangouts. This is a series that we plan to continue throughout the year, highlighting relatively recent research done either at Cornell or Princeton that hopefully is of interest to people involved with the Network Programming Initiative. And today, Praveen Kumar, who's a fifth-year PhD student at Cornell, is going to talk about some work that he did a couple of years ago with some folks from Facebook and also Lugano on wide area traffic engineering. This is some work that I think kind of characterizes the kind of thing we're hoping to do with the Network Programming Initiative. It's an idea that really came from the theory community around optimal ways to do routing in an operationally simple way. But the work itself was done in an industrial context through a series of internships at Facebook, and the demonstration of the idea was rooted in practical experience. So the way that these seminars will work, it's a little bit difficult to have interactive Q&A during the talk itself. So Praveen has about a 25 or 30-minute presentation that he'll give, and then we'll have time at the end for questions, and hopefully it's easy for people to figure out in Zoom. There's a way to raise your hand if you have a question, or we can also use the chat to have a Q&A. Okay, so without further ado, here's Praveen.
Thank you for the introduction, Nate. Hello, everyone. My name is Praveen Kumar, and in this talk, I'm going to present our recent work on semi-oblivious traffic engineering for wide area networks. This talk is based on joint work with collaborators at Cornell, CMU, Facebook, and USI Lugano. So to start with, in order to meet various competing objectives, operators of wide area networks use traffic engineering to steer traffic in desired ways. A good traffic engineering system should be able to provide high performance in terms of throughput and link utilization while being robust to failures that may arise in practice. Traffic in wide area networks have various latency requirements, such as low latency for customer traffic, but more relaxed requirements for bulk traffic, such as for replication. And a traffic engineering system should be able to guarantee these different requirements. And finally, it should be operationally simple, so that it is easy to root cause, analyze, and fix any issues that may arise in production. And traffic engineering systems must achieve these competing objectives while navigating various challenges. For example, wide area networks evolve based on predicted growth in demands, which leads to unstructured topologies and heterogeneous link capacities. Failures, such as a misbehaving router or a link going down, is common in such networks. And such failures are also difficult to predict in advance. Similarly, it is often difficult to predict traffic patterns in advance. And a traffic engineering system should be able to handle such failures and mispredictions gracefully. Also, it must take into account the various limitations imposed by the underlying hardware. For example, the number of flow rules that may be installed on routers is bounded. And finally, frequently updating the routing state in response to changes in network may lead to significant overheads. So now let's look at some approaches to traffic engineering. The traditional approach to traffic engineering relies on tuning link weights in distributed routing protocols such as OSPF, which stands for Open Shortest Path First, and ECMP, which stands for Equal Cost Multipath, so that the link weights are tuned so that they compute a good set of forwarding paths. For instance, by increasing the link weight of this edge, a network operator can steer traffic over another path. So this approach is quite simple to implement, as it harnesses the capabilities of protocols which have already been widely deployed. However, optimizing link weights in this way to achieve good performance is quite difficult in practice. And it often performs poorly when failures occur or during periods of reconvergence after link weights have been updated. So around 5 to 6 years ago, enabled by software-defined networking, or SDN, we started to see centralized solutions to traffic engineering. SDN gives us the global visibility and direct control over the network. So, in principle, we could use these capabilities to deploy the optimal routing scheme at every point in time. So one such approach to optimal traffic engineering could be based on solving the multi-commodity flow or MCF problem. And in this approach, the routing problem is encoded as an optimization problem, which can be solved using off-the-shelf optimizers such as Gurobi. However, it is not practical to achieve optimal performance using such an approach. So to really understand why, note that to actually achieve optimal performance, we would need to solve the MCF problem very frequently in response to changing demands. So as demands change over time during the course of a day, you will need to continuously solve this MCF instance, and then you'll have to update the routing scheme almost instantaneously to achieve optimal performance. Now, this is not practical because of various operational constraints. To highlight a few, let's look at the time required to solve an MCF instance. So the graph here shows the time taken by Gurobi's optimized linear programming solver to solve an MCF instance. On the x-axis, we have traffic matrices over a week. And on the y-axis, we show the time taken to solve the corresponding MCF instance. And this data is based on a real wide area network operated by Facebook. We find that it takes roughly 30 seconds to solve each instance. And this kind of imposes a fundamental lower bound on how quickly we can react to changes in the network when using an optimal MCF-based approach. Now, in addition, there is no guarantee that the solution of an MCF instance will be the same as the previous solution. So this means that we need to update the routing scheme every time we solve an MCF instance, and this leads to path churn. So again, for the same network, we performed an analysis of path churn, and we found that we would need to add or remove about 1,500 to 2,000 paths in each iteration. Now, these updates also need to be performed in a consistent manner in order to avoid any forwarding loops, black holes, and any transient congestion. And that would again impose a significant overhead on routers. So how did people actually build practical centralized traffic engineering systems? Well, let's take a step back and see what a traffic engineering system actually does. A traffic engineering system essentially has to perform two tasks. First is path selection, that is, decide which set of paths to use from a source to a destination. And the second is rate adaptation, that is, compute how to split traffic across these multiple paths between a source and a destination. So it turns out that path selection is a slow and expensive operation because you need to update many geo-distributed routers for a single path update. On the other hand, changing the splitting ratio for paths is a relatively fast operation because you need to update only the ingress router. Since we can't literally set up or tear down these global paths in response to each change, the key insight here is to modify the set of forwarding paths very infrequently, but we may change the splitting ratios more frequently. And it turns out that selecting a good set of paths is quite challenging, because we are sort of committing to these paths once computed. As in, once selected, these paths must enable us to achieve various objectives in a dynamic setting where demands change or failures occur. In particular, these paths must provide us the ability to route traffic with competitive latency, the flexibility to react to changes in demands, robustness to misprediction in demands, resilience to failures in the network, and so on. The main thesis of this work is that using a static set of cleverly constructed paths can provide near optimal performance and extremely good robustness. Specifically, we highlight that the path selection algorithm should have the following three properties. First, it should select paths with low stretch in order to minimize latency due to propagation delay in wide area networks. Second, the paths should be diverse enough to provide the ability to reroute around failures. And third, the paths should be selected in a capacity-aware and globally optimized manner in order to provide good load balancing. I'll explain what I mean by capacity awareness and global optimization in the next couple of slides. So let's look at capacity awareness and why it is needed. So consider this example topology shown here. In this topology, each link has 100 Gbps capacity, except the link from node G to node E, which is a 10 Gbps link. Also assume that all the link weights are proportional to their depicted lengths. Now, let's say we are using a shortest path-based scheme to route traffic, and nodes A, B, and C want to send traffic to node E in this topology. Now, since the path selection algorithm is not capacity aware, all the shortest paths end up using the same low capacity link from G to E. And this can lead to high congestion in the network, even though there is spare capacity. Now, let's modify our previous algorithm to be capacity aware, something similar to CSPF, which stands for constrained shortest paths first. And let's also make the link capacities more uniform. Say all the links are 100 Gbps in this case. Now assume that flows arrive in the following order, where each flow demand is 100 Gbps, the same as each link's capacity. So first, say A wants to send traffic to E, so we assign it the shortest path via G. Next, when B wants to send traffic to E, we cannot assign it the shortest path through G because the link G to E is already saturated by the flow from A to E. So instead, we route it through the next shortest path with sufficient capacity. Finally, when C wants to send traffic, we cannot use links G to E and C to F as they are already saturated. Instead, we have to take a really long detour as shown here. Now, this is clearly suboptimal because the paths were not selected in a globally optimized manner. Instead, if we had computed paths by taking every source and destination pair into account, we could have computed a much better set of paths as shown on the right here. Now, we find that commonly used path selection algorithms often do not meet all the criteria for good path selection. As an example, while shortest path-based approaches optimize for latency, as shown here, they are often not diverse enough to be robust to failures, or they do not provide options for good load balancing. Using multi-commodity flow or MCF, we can optimize for good load balancing, but we find that this can lead to paths which are brittle to failures, or they often have higher latency. So previously, people have tried using demand-oblivious schemes such as variant load balancing, or VLB in short, in order to achieve good performance. So let's look at VLB and oblivious routing in general in a bit more detail. VLB works by routing packets to destinations through random intermediate hops. The sender simply sends packets to all the other nodes at random, and these nodes in turn forward the packet to the final destination. VLB has been shown to balance load very well in mesh networks while being robust to failures. It has also been applied in the context of wide area networks. However, wide area networks do not have mesh-like topologies. So while VLB still provides good robustness in this case, it often leads to very long paths, especially when the source and the destination are close by. For instance, imagine sending traffic from Seattle to San Francisco via New York. This also leads to high link congestion and hence degraded performance because the same traffic contributes to utilization to more links. Oblivious routing, which was proposed by Räcke in 2008, generalizes VLB to non-mesh topologies. It does so by providing a hierarchy of intermediate hops instead of a single intermediate hop. It iteratively computes a distribution over routing trees called a randomized routing tree. And each routing tree is computed using an approximation algorithm that guarantees that the path lengths in the routing tree are close to shortest paths. Also, in each iteration, the weight of each link is adjusted based on how much the link has been utilized in the previous set of routing trees. So this ensures that no single link is overutilized when we consider the entire ensemble of routing trees that are generated. This, in turn, results in a set of routing trees that provide good load balancing while being diverse enough to be robust to failures and also ensuring good latency. And hence, we find that oblivious routing meets the criteria for a good path selection algorithm. The oblivious routing scheme thus generated has been shown to be log n competitive with MCF. What this means is that no matter what demands arise in practice, the maximum congestion that you will see with oblivious routing is guaranteed to be within a log n factor of the optimal, where n is the size of the network or graph. So while this log n competitive performance with respect to optimal MCF is a very powerful theoretical result, it still needs over-provisioning your network by a significant amount. So the question is, can we do better? The short answer is yes, and let's see how. Now, going back to our traffic engineering model of static path selection and dynamic rate adaptation, SMORE proposes using oblivious routing to select paths which are low stretch, robust to failures, and provide good load balancing properties. SMORE combines this with dynamic rate adaptation. It uses linear programming to dynamically optimize the splitting ratios which are used to map traffic to paths in order to achieve better performance. This approach of semi-oblivious routing has been previously shown to be not significantly better than oblivious routing in the worst case. However, these worst case scenarios consisting of artificial traffic matrices and topologies don't really occur in practice. In fact, as topologies evolve in response to estimated demands, link capacities and traffic matrices are often correlated. So the natural question to ask is, how well does semi-oblivious routing perform in practice? So to analyze the performance and robustness of SMORE, we performed extensive evaluations using data from Facebook's wide area network. This network follows a common network design for content providers consisting of several large data centers and points of presence spread across the globe. Traffic on this network consists of both latency-sensitive traffic, such as the customer-facing traffic, and background elastic traffic, such as for replication. So we collected accurate snapshot of the network consisting of topology and traffic matrices for over a month, and we performed high-fidelity simulations to study performance and robustness characteristics using our simulator called Yates. To compare with other traffic engineering systems, we implemented a wide range of systems ranging from traditional ones to recently proposed approaches. We also implemented an optimal traffic engineering system based on MCF to serve as a baseline. This optimal scheme assumes that there are no operational constraints and it could use any arbitrary number of paths to route traffic. Note that it is not practical to implement such an optimal TE system, but we just use it to set a baseline. So let's look at performance of these systems on Facebook's wide area network. We will look at metrics of throughput, maximum link utilization, and any drops due to congestion in the network. The x-axis here shows time over half a week for each traffic engineering system, with the traffic engineering systems shown at the top. And the y-axis shows the normalized value of throughput, maximum congestion, and any drops due to insufficient link capacities. For instance, a normalized throughput of 0.8 here means that only 80% of the entire traffic could be delivered. So when using the optimal approach that is on the left side, the optimal approaches uses MCF to minimize the maximum congestion, and we find that the maximum link utilization varies between 40 to 65% following a diurnal pattern. This value is shown by the green lines in the figure. So without going into the details of each of these results here, the main observation is that other schemes, with the exception of CSPF, Oblivious, and SMORE, saturated at least one link in the topology, and this led to decrease in total throughput. So we see that the black lines representing normalized throughput are below 1 for such schemes. In addition, SMORE performs closest to optimal with maximum link utilization shown by the green lines within 16% of optimal on an average. We performed a similar experiment to measure robustness of these traffic engineering systems on Facebook's wide area network. In this experiment, we failed a unique link every hour and allowed the traffic engineering systems to react to such failures. So as expected, optimal traffic engineering is able to reroute around most failures, but at the cost of increased link utilization or congestion. We see similar increase in congestion for other schemes as well. And again, SMORE's performance remains closest to optimal while maintaining almost 100% throughput. Now, these experiments were done with a path budget of 4. That is, we allowed each traffic engineering system to use up to 4 paths for each source and destination, except for optimal, which could use an arbitrary number of paths. So we find that on increasing this path budget, other schemes, such as those based on case shortest paths and dynamic rate adaptation, also start performing close to optimal. However, they require a much larger number of paths. For instance, in this case, the approach based on case shortest path and MCF took about 8 times more number of paths compared to SMORE. So thus, SMORE is able to achieve good performance in the presence of operational constraints. The paper discusses more operational conditions that arise in practice in more detail. Now, a natural question to ask is whether these results are specific to Facebook's workload, or do they generalize well over other topologies and traffic matrices? So to answer this, we performed large-scale simulations using our simulator Yates, using topologies from Internet Topology Zoo and other ISPs. We generated a large number of traffic matrices using the gravity model and modeled various operational conditions. So while we did see some variation in performance across different topologies and operational conditions, we found SMORE to have better performance and robustness in aggregate. For instance, this plot on the left shows normalized capacity, where capacity is defined as the factor by which we could scale up the traffic matrices before we found that at least one link was saturated. The values shown here are normalized with respect to optimal traffic engineering, and we find SMORE to be quite close to optimal over these set of topologies and traffic matrices. We also measured the probability of achieving different levels of availability SLOs as shown in the figure on the right. The x-axis shows the availability SLO. That is, we want, when we say the availability SLO is 99%, that means we want to have throughput greater than 99% over a long period of time. So the x-axis shows the availability SLO, and the y-axis shows the probability of achieving the SLO for different traffic engineering systems. We again found SMORE to be quite robust to failures as compared to other traffic engineering systems. So to summarize, we found that path selection is critical to the performance and reliability of traffic engineering systems. Semi-oblivious traffic engineering, which combines oblivious routing for path selection with dynamic rate adaptation, meets the competing objectives of traffic engineering by providing near optimal performance and high levels of reliability. And finally, we have made our implementation open source on GitHub, so feel free to check it out. And this talk was based on 2 papers mentioned here. Thank you, and I'll be happy to take questions.
Okay, so I think the way we'll do this is if folks have questions, if at the bottom of the Zoom participants window, there's a raise hand button. So if you have a question and raise your hand, then I can call on you and you can speak up. So we have a physical raised hand here in Ithaca from Dexter Cozen, so we'll start out with that.
In the BLB approach, you mentioned that there's one hop that's chosen randomly, and then it was forwarded on to the destination. And the problem with that was that a lot of traffic goes to close nodes, and you may actually end up sending it too far. And I'm wondering if anybody has investigated adjusting the probability distribution to take that into account. So in other words, if you know something about the topology of the network, you can favor nodes, closer nodes, to counteract that detrimental part of the algorithm.
Right, indeed. So the question was that VLB, as I mentioned earlier, will lead to longer path latencies because we are sending it via intermediate hubs, which may be quite far from the source and destination. So is it possible to assign probability distribution over these paths by taking the topology into account? And let's say you give higher probabilities to shorter paths versus lower probability to longer paths. Right. So I'm not aware of any specific work which has investigated that, but oblivious routing, the Räcke's algorithm, kind of does the same thing because it generates these low stretch routing trees, which give higher probability to shorter paths. And as these paths are being used up, you will start finding longer paths, and the longer paths will ultimately end up getting lower probability. But I'm not sure of or aware of any particular other paper that has explored this.
So I have a question as well. It's kind of a high-level question. There's been some contemporary work by Manu Kobadi at MIT and folks at Microsoft looking at traffic engineering when you have the ability to vary the capacities of the channels dynamically. And more broadly, there's, I think, growing interest in kind of stochastic or probabilistic approaches to traffic engineering. What do you see as the bridge to actually seeing some of these things getting into practice? Or maybe to say it another way, what would be the hurdles if you wanted to take these algorithms and not just do simulations, but actually try to deploy it? What challenges would arise? What kinds of operational concerns might you have?
Well, one thing is that if you look at SMORE or oblivious routing in particular, it doesn't take this particular approach does not take into account these variable link capacities. So there might be some ways theoretically to optimize or compute these oblivious set of routing paths, which take some noise level or some margin in link capacities to generate these oblivious set of paths. And in terms of hurdles in practical deployment, I guess one of the main things is how fast do we want to optimize the traffic engineering system in response to any changes, even changes in demands or changes in link capacities. Now, there's this trade-off here that if you update the routing scheme very frequently, it might interfere with your transport layer. For example, if you're using TCP congestion control, you need some time for it to stabilize. So you need to not update the routing scheme too frequently. On the other hand, you can't wait too long to update the routing scheme because your scheme might become suboptimal after a certain point of time. So finding this right balance or right granularity of updating the routing schemes could be one key approach, one key point in making such schemes practical.
We have another question in the room here from Hardik Soni, who's a postdoc.
So I have one question on the result slide of the first result slide. So maybe I missed something here, but what is the exact difference with comparative difference with CSPF here? Because
So is the question about CSPF versus SMORE versus optimal in this case? So here, CSPF is able to route 100% of the traffic, and the maximum link utilization is less than 1. This is because we configured CSPF to keep 20% headroom. So whenever a link was 80% saturated, we started to migrate traffic to other set of links. So we see the maximum link congestion around 80%. And since CSPF will always route traffic over paths which have sufficient capacity, the maximum link congestion will always be within 1. But the problem with CSPF that is not shown in this result is that since it is always trying to find these paths with sufficient capacity, it might end up taking really long paths. And this leads to increased latency.
Right. Well, if folks don't have more questions, I think we'll wrap up here, and we'll be announcing the next the next iteration of our seminar in a few weeks, and it will be a PhD student from Princeton, and we'll probably alternate between the two campuses going forward. So thank you so much for participating, and hope to see you on a future call. Thank you.